Keeper 2.5, applications of differential equations. In this keeper, we're basically going to do more logistic growth, do some solving differential equations, and even in your homework you might have slope fields and stuff like that. It's basically putting everything that we've learned together into specific application problems. All right, so example 1, it says suppose the population of bears in a national park grows according to a logistic differential equation dp over dt equals 5p minus 0.002 p squared, where p is the number of bears at time t in years. It says given that p of 0 is 100, find the limit as t approaches infinity of p of t, and then sketch the graph of p of t. All right, so the first thing I'm going to do is I'm going to rewrite my differential equation. And so they gave it to us in just kind of like a quadratic type form, but I need to rewrite it into a logistic form. So what I'm going to do is I'm going to factor out a 5p from both pieces or both terms, and I'm left with 5p times the quantity 1 minus p over 2500. Now that it's in my logistic form, I can clearly see that my carrying capacity is 2500. Remember, the carrying capacity is whatever's under the p. So if my carrying capacity is 2500, the limit as t approaches infinity of my population, like what's the population limit? The population limit is 2500. And we can see this if we did it graphically. If we sketched a graph of this, we're starting at 100 and I'm going all the way up and I'm curving around like the logistic model does, and it levels off at 2500 since that's our carrying capacity. All right, so given that same exact problem, it says for what values of p is the solution curve increasing or decreasing? Well, again, looking at my graph, I see that's increasing from the initial population all the way to the 2500. So 100 is less than p is less than 2500. And then it's decreasing, again, if I go over that 2500 for whatever reason. If population starts to boom a little bit over 2500, you know that we're going to have probably deaths in the bear population to cause it to go back to our carrying capacity of 2500. So anytime we're over 2500, we're going to decrease back down to our carrying capacity. All right, so in example 2, same situation, except for this time they're giving us an initial population of 1500. And so again, working with that differential equation and rewriting it by factoring out the 5p, I get that my carrying capacity is still 2500 regardless. So what I'm trying to show you guys is that it doesn't matter what your initial population is, your carrying capacity is still your carrying capacity. Whether you start with 100, whether you start with 1500, you still can only grow to a certain population size. So the limit as t approaches infinity of p of t is still 2500. This time our graph looks a little bit different because we're starting over our inflection point or over half of our carrying capacity. We're just going to kind of curve straight upwards to that carrying capacity and leveling off. All right, so given that same situation, when is it increasing, when is it decreasing? Well, it's increasing from our initial all the way up to our carrying capacity. So it'd be increasing from 1500 to 2500. And then again, if by chance it goes over the 2500, it will decrease back down to that carrying capacity. All right, example 3, we have the same scenario, except for this time our initial population is 3000. So they want to know the limit as t approaches infinity of p of t. Again, if I work with that same differential equation and rewrite it, I see that my carrying capacity is still 2500. So this time, even though my initial population is over my carrying capacity, my carrying capacity is still yet going to be 2500. So that means our limit over time is still going to be 2500. This time, though, if I look at it graphically, I'm starting above my carrying capacity, which means I have to decrease down to my carrying capacity. So I have kind of like a curve concave up going down to that carrying capacity. Now again, looking at that graph, where is it increasing or decreasing? Well, it's decreasing to start this time since we started above our carrying capacity. So from 2500 to 3000, it's going to decrease. And then once it gets underneath that 2500, it's going to increase back up to the 2500. So anytime your population is less than 2500, it's going to increase back up to the 25. And then when we were above the 2500, it was decreasing. All right, so example 4, but again, same situation. It says, well, how many bears are in the park when the population of the bears is growing the fastest? Well, again, you want to kind of think about your generic or general logistic growth model. And so that's going to happen at half of your carrying capacity. So again, if our carrying capacity is 2,500, it's going to grow the fastest at half that population, which is 1,250 bears. And again, I can look at it as that's where my inflection point is, or I can look at it as that's half of my carrying capacity. All right, so example 5, it says the population of animals is modeled by the function P that satisfies the logistic differential equation d of P over dt equals P times 1 minus P over 100, where T is measured in years. If P of 0 is 20, solve for P as a function of T. So again, they're asking us to solve this differential equation. The first thing we need to find is our A. And so if you remember, our A is our carrying capacity minus our initial population over our initial. So 100 minus 20 over 20 is 4. And then I'm going to plug that into my solution equation for logistic models. And so I get P equals the carrying capacity of 100 over 1 plus A, which is 4, e to the negative little k was 1, so negative 1t. All right, so continuing on with that example, it says use your answer to part A to find P when T equals 3. Give exact and decimal approximations. So when P equals 3, I have P of 3 equals, and all I'm doing is I'm plugging 3 in for T. And so I have 100 over 1 plus 4 e to the negative 3. And that would be my exact answer. But once I plug that into the calculator, I get 83.393 animals, or approximately 83 animals. All right, example 5 continued. So if just keep going with that same scenario with the animals, it says use your answer in part A to find T when P equals 80, and again give your answers as exact and approximations. So this time, if P equals 80, I have 80 equals 100 over 1 plus 4 e to the negative t. I'm going to multiply both sides by 1 plus 4 e to the negative t and divide by 80. So I get 1 plus 4 e to the negative t equals 100 over 80, which is really just 5/4. I'm going to subtract 1 on both sides to get 4 e to the negative t equals 1/4. Dividing by 4, I get e to the negative t equals 1 over 16. Ln both sides, I get negative t equals negative ln of 16, or t equals ln of 16 years as an exact answer, or t equals 2.772 years as a decimal answer.